Hi, in this video we are going to see another example of solving a problem using combinational blocks. Okay, so now our problem is that we have two rooms where we carry out two experiments, and for some reason we need to know in the maximum temperature that is achieved in either of the rooms. So we want to design a circuit that takes the temperature in room 1, sensed by a sensor, temperature sensor there. It also takes the temperature in room B. Temperatures are fairly cold. These goes from 0 to 9 in these inputs here. And then our system has to detect which is the maximum temperature and display it in a 7-segment display. So basically what we want to have is something like a box. I draw it here. We want basically a box with our 7 segments display here, more or less. Okay, and to that system I will connect my inputs. Okay, TA, TB, 4 bits inputs, TB, that will, and I will read the temperature, the maximum temperature in the 7-segment display. Okay, it will display number 7, for example, or like this, for example. Okay, play number, temperature is 7, 6, 8, whatever. Okay, so basically we have the output, the device, the 7-segment display is a component that we can buy in an electronics provider, and our circuit takes the temperatures and generates the 7-segment representation for the temperature which is the greatest between these two. Okay, so to do that we basically follow the methodology that we use when we use subsystems. Okay, it's a lossy methodology that that is a general idea. Okay, we have our description, then we decide which blocks we are going to need. Okay, see, if my problem is very complex, I may have to define new blocks that are a bit more simple and then solve each of those blocks as a new problem. Okay, until the point that I can identify the functionality with the standard blocks. I can identify that I have to do tasks that can be done with a multiplexer or a decoder, comparator, or whatever. There may be some functionality that is not very clear, but if that functionality is small, I have to calculate a bit depending on 2-3 other bits. We can use the generic method of the kernel map, for example. Okay, and then once I have solved all the blocks, then I connect everything together, and yes, we can draw the circuit. Okay, so in this example we know that we have to compare these two numbers. Okay, to do that we will use a comparator. Okay, and then after we compare the two numbers, we will have to we identify that. Okay, we will have to compare TA and TB, so I will need a comparator somehow. Okay, then depending on the result of the comparator, I will have to decide if I convert the to 7-segment, the temperature in A or the temperature in B. I will have to select which is the greatest of temperatures. Okay, so I have to select TA or TB. To select that, I will use our selection module, which is the multiplexer. And once we have selected which is the highest temperature, I will convert that temperature to a format that can be displayed in a 7-segment display. So I have to convert from a regular binary number, because our temperatures are regular natural binary numbers, to 7-segment encoding. This is a code converter. Okay, we need to convert from natural binary to 7-segment. This is a binary to 7-segment converter. These are modules that we are going to use most likely, okay? And also the selection of TA and TB will be done as a result of, depending on the result of the comparison. Okay, so somehow we will have to connect the output of the comparator to the selection inputs of the multiplexer. Okay, so with that we can draw a possible depiction of my circuit. So the idea is that I will have a comparator, okay, to compare TA and TB. And then depending on the result of the comparator, I will select with a multiplexer. Okay, so I'll draw a box here. Not here. And then my multiplexer will select which is the maximum temperature, and that maximum temperature I will have to convert to 7-segment. So I will use that block here. Okay, now this is the idea. I have TA and TB going into my comparator. Okay, this goes to input A and to input B of the comparator, and then the outputs are the greatest, the A is greater than B, the equal output, and the less than output. So I consider a standard comparator without cascade inputs. Okay, this is a well-known module. We know these modules are available in as discrete devices. It will also be available in our library of devices, no matter the style of design that I do. Okay, and if I decide to make a version of this design using Verilog, for example, I know in Verilog we have comparison operators. Okay, so we can represent it very easily. So this is a standard module. We don't have to go to design the inside of the comparator. Okay. Now, this is a MUX multiplexer with inputs 0 and 1, and we have just one selection input over here. So we know that the multiplexer should select in temperature TA or TB. Okay, so for example, we will input TA here and TB here. Okay, in fact, this multiplexer is a multi-channel multiplexer, okay, because TA is 4 bits and TB is 4 bits. We will generate a representation of maximum temperature with 4 bits altogether. Okay, so this symbol actually represents not one but 4 multiplexers, one multiplexer for each bit of TA and TB, but all the multiplexers are controlled by the same control signal, okay, as we have seen in the slides. So TA and TB are inputs. Actually, TA will be connected here. Okay, TA, I could have drawn connection here like this, and for TB, I could have drawn a connection here as well. But it's not really necessary. We can just put the names, and this is called a connection by name. If I repeat the name of the input, we assume that it is physically connected, okay, because I'm using the same name. So it is a method not to make the drawing too complicated. Okay, now we will make the selection TA or TB depending on the result of the comparison. Okay, we'll leave it for later. And then once we have the maximum temperature, it will go to our binary to 7 segments converter. And that's it. This is also a standard module we have seen in the slides. Okay, and this is something that I can then directly connect to my 7-segment display to have my number represented. Okay, more or less. Great. Now the only thing that remains is that somehow I have, from the result of the comparator here, I have to, depending on the result of the comparator, I have to make the selection in the multiplexer. It's not really difficult indeed. Actually, we can do it in 2 different ways. Okay, this is the greater, I call it G, the equal, and the lower outputs of the comparator. Okay, so what I use here in the, let's call it S, the selection input, will depend on this G, E, and L. Okay, we could define that problem as a generic problem. Okay, I'll say I have some kind of circuit that have to calculate the value of S depending on L, E, and G. Okay, and then I would say I could write a truth table or a kernel map and analyze all the cases. I would say, okay, if G is that, if I have that value, then it means the number is bigger. I should select that. So I use a 1 or a 0 for S. We could do that, okay, if we don't have it very clear what must be the selection in each case. But it's not really necessary here because we have enough information. For example, what we want to do, we want to select the highest temperature. Okay, so consider if we use the greater as the selection input here. Okay, when A is greater than B, G will be 1. If I use it for S here, then S will be 1 and we'll select this input. We'll select input where I have put temperature B, but it's not what I want. Okay, if A is greater than B, I want to select TA, so I can try with the lower output. Okay, so when it means when A is lower than B, so it means B is greater than A, TB is greater than TA. Okay, this will be 1. Okay, if I use it for the selection input, okay, then the selection is 1 and I will be selecting TB. TB will go to the output of the multiplexer, will be converted and shown here. Okay, so this will solve my problem. Okay, just using the lower. If both temperatures are the same, okay, I still want to display here what's the maximum temperature. But in that case, it doesn't matter if I display temperature A or temperature B because both are the same. So when both are the same, this is 0. This will select temperature A, which is perfectly fine because it's the same than temperature B. Okay. Okay, so this is with this option would solve my problem. There are many other options actually, because we could have selected the gritter signal to control the multiplexer, but in that case we have to swap the inputs of the multiplexer. Okay, this is also a good solution. Okay, when A is greater than B, it becomes 1. I select TA. When A is not greater than B, it is a 0. I select TB. Okay, so this is also a possible solution. Okay? No matter really what you use. Okay, I will leave that solution instead of the other. So it solves part 1 of my problem. Now, the next point is that we want to add some indicator to know in which room we are reaching the highest temperature. So in the box of my device, I want to put two LIDs, one here, and two that will be activated. This will be activated when the maximum temperature is in room A, and this will be when maximum temperature is in room B, right? Also, when it says when temperature is greater or equal than TB, it means that if both rooms have the same temperature, we should activate both LIDs in this case. Okay, now, so this is A, section A. For section B, we'll make some changes here. We'll make some additions that we'll write in green color. So now our problem is that we also want to generate signals LA and LB. And the problem is similar, okay? We'll activate LA when A is greater than B. And we'll activate LB when B is temperature in B is greater than in A. Okay. Imagine we could solve that problem by saying, okay, activating LA or LB will depend on the temperatures. Okay, so we could think on a box that may calculate the value for LA and the value for LB depending on the temperatures. TA and TB, they actually depend on that, but each temperature is a number of 4 bits, and these are two functions. We should have to solve that problem. If we do it as a generic problem, then it's a function simplification or function minimization using 8 inputs. It's an 8 input kernel map, which is something quite crazy. Okay, it's something that you don't want to do. Okay, but you don't really need to do that because you already have the result of the comparison of comparing TA and TB. So you don't really need to use the numbers because the comparator has done most of the job for you. So you can actually think of this problem as a problem of calculating LA and LB depending on the result of the comparison. Okay, but these are only 3 bits, and this is something that you can do as a generic problem. Okay, here you can think of it as a general problem you can solve with kernel map, but because this is only 3 inputs. Okay, so we will do it with a kernel map. This is a 3-input kernel map for LA, another 3-input kernel map for LB. But the main idea is that to complete our problem, we have used some standard blocks. Let's make some room here. We have used some standard blocks, but now we have identified I will move it here. I'll make a copy of it better. So we have identified that we can design a specific block that will give us the results that we want for LA and LB, okay, by connecting these signals here. By connecting here, the equal signal will be connected here, and the lower signal will be connected here, okay? So we have now a new block that we have to solve, but this is simple enough to be solved with the kernel map. This is just an option. It is not really necessary to do it like that, okay? You can think on other options, but this is not a bad solution. So we have G, E, and L, G, E, and L. And that's it. So I want to connect LA whenever the maximum temperature is in TA. It includes when the output is, the G is active, okay? Because when G is active, it means that temperature in A is greater than the temperature in B. But it also includes the cases when the temperatures are equal. So when they are equal, also the maximum is in room A. It's in room B as well, but it's also in room A, okay? So we include the greater and the equal. For LB, we have to consider when it's lower, when temperature in A is lower, so it means when lower is 1, but also the equal here and here, okay? And we can solve it with, we can calculate that like this, for example, as a sum products. You could also use a product of sums. It's going to give the same result, actually. You can try. So it will be A is equal, this is G plus this is E, okay? And this is equal to E plus L, okay? So it's actually, it's really obvious. I have done it by defining the whole problem and resolving it in a systematic way for you to show how you can do it, okay, in a generic problem. But it was really very obvious how it's finally solved, okay? I will remove this part here because the idea is that, try to delete this one. Oh God. Okay, so because the idea is that I activate LIDA when greater or equal, so the expression is actually very intuitive, okay? I just need an OR gate to do that, okay? When LA, when temperature in A is greater or both temperatures are equal. And in LB, I activate it when temperature in, using also an OR gate, when temperature in B is greater or both temperatures are equal. Okay? We may have arrived to that solution just by understanding what's going on. But even if you don't have very clear what's the dependency between the outputs you want and the data you have, if you don't have it very clear, you see there are many options. If the number of signals is not very big, you can always do it in the as a general problem, okay? And use kernel map and you will be sure that you will get an optimum design for that. Okay. Okay, so that's it. That solves our problem in that case. Of course, you can solve this part using other options, maybe using a multiplexer, maybe using a decoder and some gates, any way you may think about. Okay, but I think it's a convenient and clear enough option to solve the problem. Okay, that's it. Thank you.